Hello, everybody.
Good morning, sir.
Good morning, sir.
Good morning.
Good morning, sir.
Good morning, sir.
Okay, so yesterday, just a minute, let me share it first. Okay, so yesterday we started with the basic introduction of the finite element methods, and what we understand so far is we have the big problem. I give example of an aircraft, yeah, and then what we do, the big problem we divide into many small problems basically. So we divide into a smaller domain, and under the smaller domain we solve the problem locally basically, although it's not locally, basically all are connected, so final solution is the actual close to the actual solution. However, the idea is to concentrate on one element, and based on that we build up a system, and that system is a matrix system. We call it Ku equal to F, where K is the stiffness matrix, U is the displacement vector, and F is the force vector. Yeah. Okay. Now, now the thing is how to build those matrix systems. Yeah. So that is what the finite element methods is all about. Okay. Now, the simple example of, let us say, instead of the aircraft, which is very complicated, we can also have, let us say, a beam, a bar, which has a variable, area, and this has to be modeled. Let us say this is the force F. So this is variable area. It may be difficult to find out what is the displacement here. So unless we do some kind of some method we need to calculate the stresses or displacements fast. Okay. Now, what how we do this? Okay. So as I said, we will do it many ways, and one of the things is we can, for example, we can visualize this in this term. Depending on the area, we can take a bar which is like this, bigger. So what we are doing is uniform. So these are our elements. You see one element, which is the area is changing. So what I'm doing, I'm putting a bar, several bars of the uniform cross section, and putting in series, and then we can solve. We know that if this is L1, this is L2 is the length, this is the Li. So accordingly, we can, let us say they are made of the same material, so we get K1 equal to E A 1 over L1. So area is this has area A1, this has area A2, and so on. Or Ki is equal to EAI over Li. Yeah. Okay. Now this is what we see here is Ki, the stiffness we calculated, and that really means this is equivalent to the several spring. So 1 spring, 2 spring, 3 spring, 4 spring, and so on. So depending on, we have the K1, this has K2, K3, K4, and so on. And then you can find the answer. You can also find out the displacements. What is the value of? So let us say this is a node number 1, node number 2, node 3, 4, and so on. Node, this becomes U1 equal to 0, then U2 equal to what you can calculate. All of them you can calculate, right? So this is very basic. So this is the direct method. Direct method we are using, meaning that what we are doing, we are not solving a differential equation. We just based on some mechanics, we are solving this a problem which has variable cross section, and in order to solve it, we have divided into subdomain, and for every domain, what we did, we calculated the average area. We have the length, material property E we know. Based on that, we have calculated K1, K2, K3, and after that we solved it. Okay. Now for the same problem, you have like this. Yeah. So you have, for example, we say this is U1, this is U2, U3, U4, U5, and then there will be a force F5, let us say, is the force, right? So F5, because at the end, we have a force here, F. So at the end, somewhere we have the force F, at the end we have force F, right? So we have the force applied here, we assume, we write it as F1, this is F2 is the force, F3 is the force, F4 is the force, F5 is the force. So when we say Ku equal to F, in this term, what it means that U is equal to nothing but U1, U2, U3, U4, U5, right? Okay, where U1 equal to 0, right? So we have the 0, then U2, U3, U4, U5, right? So we have this, yeah? Okay, now given this displacement, for this one, for F, we can also find out. So in this case, F is equal to whatever force we apply on this system. So F1, we have F1, we have F2, we have F3, we have F4, we have F5. So here there are 5, this is an example where we have 5 degrees of freedom. So we have that. Now only thing remaining is what is the value of K. And for that, we have to now we have to now see that if we have only one spring, in that case, what it will be. So if there is only one spring and we have the force like this, then we have a Ku equal to F also here, U equal to what we have, this is U1, which is equal to 0 because fixed, this is U2. So you have U1, U2, and this is U2 equal to, let us say, right? So it will be 0 U, right? Okay. Then what you have is we have the displacement vector. We have the displacement vector, and then we have the force F is equal to this F1 and F2. So let us say there is a force applied here. Of course, there will be force applied because of the reaction force, which is the force we are talking about. So let's call it F1, and then let's call it F2. So this will be F1 and F2. Of course, we don't know what the force here because this is fixed. We know displacement 0, so either we know displacement or force, but not both. So 0 we know for sure because it is fixed, U equal to 0. But F1 we don't know. We don't know. Actually, from mechanics we know, but mathematically we don't know. Yeah. So this F1 we have to find out. F2 is equal to F is given, right? So in this case, it will be F1 we have to find out, and F2 equal to F. Right? So this is the force vector for this one. So this is given. Now, only thing is, what is the stiffness matrix, right? So K, the stiffness matrix. Okay. So stiffness matrix K. Okay. Now, K will have K11, K12, K21, K22, right? Okay. Now, K11, K12, K21, K22. Now, looking at this, what we have to find out Kij, right? Now, Kij is in case of a, let us say this is I, this is jth node. So, and what is there? It will have two things. So one is U. So this is Ui. So this is Fi. Yeah. And this one is Fj. The two forces applied, and there will be a displacement Ui, and there will be displacement Uj. Right? Okay. Now we can maybe write a small letter F. Okay, so that will be probably better. Yeah. Okay. Now, so Kij is equal to force required to induce unit force required at degree of freedom I. Let's do like this one. I. So force required at degree of freedom I to induce unit displacement at Z. Yeah. Or we can also write other way around. Force required at degree of freedom J to induce unit displacement at I. Yeah. So what is the meaning of that? While let me complete it. While keeping other degree of freedom fixed. Okay. So force required at degree of freedom I to induce unit displacement at J. Okay. While keeping other degree of freedom fixed. Which one? Like we are just talking about I and J only, and in this case only two. So if we have more degree of freedom for the same element, then we have to fix others. So what is the meaning of that? So let's look at that. So we have one spring. Okay, and say this has this is the ith spring, let us say, so or K only, and we know that this is U1, this is U2, and this is F1, this is F2. Okay. Now, how will we, as per the definition, if you want to find out K is equal to K11, K12, K21, K22. Okay. So first K11. So what is K11? K11 is force required at degree of freedom 1, yeah, to induce a unit displacement at node 1, the node or a degree of freedom 1 and 2, right? It has single degree of freedom per node. So either we call it a node or we call it degree of freedom, right? So both are same because it has only one degree of freedom per node. So, and those degree of freedoms are U1 and U2. So as per definition, this one, force required at degree of freedom 1 to induce unit displacement at degree of freedom 1, at degree of freedom 1. Yeah, or you can say also node in this case because only one node I and node J. Okay, while keeping other degree of freedom fixed. Now here, what we are talking about? We are talking about we want to find out a force which is required at node 1 to induce a unit displacement, at node 1. Yeah, okay. So, and keeping other fixed. So other fixed is 2 is other degree of freedom means here 2 because we are talking about only 1 and 1 only. So what it says that we fix this one and then we are applying, we are moving this y u1 equal to 1 and then we want to find out what is the force. So what is the force required to have displacement equal to 1? And we know that in this case, if we fix at one end, the other point is fixed, then what happens? We have K equal to Ku equal to F. We know that, right? So when we fix one end, then we know that this is the equation, right? Okay, so now K is there, and then U equal to F. But here, in this case, our force here is F1, right? So this is F1. So actually we write K U1 equal to F1. This is the equation, actual equation, because we are talking about F1 and U1 terms only. The other point is fixed. So we are just talking about this one. Now, given this, the F1 is equal to what? K11 by definition, right? So K multiplied by 1 equal to K11. Because K11 is the force required to induce a unit displacement here. So U1 equal to 1, K times 1 equal to K11. So that really means that K11 equal to K. Simple. We got that. Okay. Now let's look at what is value of K12. Let's go. K12 is, let's go back to the definition. Okay. Now remember that I and J are interchangeable. Okay. You can talk the same way. Okay. So now force required at degree of freedom I to induce unit displacement at degree of freedom J while keeping other degree of freedom fixed. Now, what is the meaning of that? Force required at degree of, when say K12, this means I equal to 1, J equal to 2. So force required at degree of freedom 1, yeah, to induce unit displacement at degree of freedom 2, right? Okay. So, well, we can see here. We can also do like this one. Instead of going by definition, we can also do like this. This is the original configuration, right? And we are applying u1 equal to 1. So this becomes like this, compressed, right? So what is the value? Here we have from here to here is u1 equal to 1. And what is the force required? This one is force required will be K, what we call it K11 is the force required to have displacement equal to this. If K11 is and K11 is the force basically, right? This is the force required. If you look at here, since there is a force here equal to K11, there has to be a, so K11 equal to K is the force. As per definition, K11 equal to K. If force is K, there will be another force which will be in this direction, the opposite direction, right? And okay, so because we know that in order to have equilibrium, if the force here is F, the other side also force will be equal to F. So if this side is K, another force which will be acting on the spring will be K only, but it will be in opposite direction. Yeah, so what is this K? This K is force required at node 2. See here, this is node 2, this is node 1. Right? So force required at node 2 to induce the displacement at unit displacement here. But so what is the value of this? This is the K force that you need to induce a unit displacement here. Go back to the definition. What is that? Force required at degree of freedom I. We are talking about degree of freedom in that case 2 to induce unit displacement at degree of freedom J. J in our case is 1. So while keeping other degree of freedom fixed. Now, what happens here? This is, this tells you K21 equal to minus K. By definition, the force required at node 2 to induce a displacement, unit displacement 1 is K21, and K21 is equal to minus K. Minus K, why? Because this is opposite X direction. So K21 equal to minus K. Similarly, you can work the other way. Yeah. So we can have like this. Now we have like this. What we are doing now, we have to find out K22. K22 is the what? Force required at node 2. So this is degree of freedom 1. This is the degree of freedom 2. Okay. Now K1, the point 1, then point 2, and K12, K22 is the force required at node 2 to induce a unit displacement at node 2, while keeping all other degree of freedom fixed. So 1 is fixed, and you are applying a unit displacement. So U2 equal to 1, and hence what is the definition? This is K. So you have K U2 equal to F2. Yeah, so K times U2 is equal to 1 is equal to, by definition, it is K22. So K22 equal to K simply. So K22 equal to K. Now, if you apply that really means in this case, the value is here. If U2 equal to 1, then K22 equal to K basically we are getting here. And the force, opposite force will be, in force here will be opposite. So if it is K here, it will be K, but the opposite direction. And hence, K12 will be minus K. Why? K12 means what? the force required at node 1 to induce unit displacement at node 2, right? So hence this is the k minus k because the force is in the opposite x direction. Yeah. So finally, what do we get? We get k equal to k11, k12, k21, k22, and those values are, sorry, these are nothing but k minus k minus k. Any question, guys, so far? Any questions?
No, sir.
No. Okay.
Sir,
Yeah.
if you could please again explain the direction here. I got confused.
Which direction?
That
That's
positive k and minus k. Can you just recap it a bit?
so. Okay. See here, guys. So if there is a spring here, yeah, and if you are fixing it here, and here, if you apply a force F here, what will be the reaction force here? So if F here the reaction force has to be in the opposite direction. Why? It's also from the Newton's third law as well, right? So if you are pulling it this way, there will be a reaction will be which will be opposite, right? So that this is imbalanced, otherwise it will move, right?
Okay. So every force
Right.
that is applied is accompanied by a reaction force, which results in a negative k.
Yeah.
Okay, sir. Thank you, sir.
Got it. Yes. Any other question? Yeah. Okay. So we have this stiffness matrix. Okay. So at least for a very simple system, we have a system where a single spring is there, regardless of what kind of problem is, regardless of whether our problem is this, or our problem is this, or our problem is this, or our problem is this. All of them we can solve just by using ku equal to f, and where in all cases this is 1, this is 2, this is 1, this is 2, this is 1, this is 2, this is 1, this is 2. Yeah, this is u2, this is u2, this is u1, this is u2, this is u1, this is u2. Only thing is, you will see here that in this case u1 equal to 0, u2 you don't know, but there is a force given. So either displacement is given or the force is given. It cannot be both. So at node 1, displacement will be 0 because it's fixed, but force we don't know. Yeah, you know as F physics, otherwise you don't know, right? Since you know that force here will be equal to this one, otherwise it's not given to you. You have to find out, but force is given unless you know. In this case, force is needed. Otherwise, typically the problem will have a force given so that you find out the displacement. Otherwise, the trivial, right? Okay. So here also u1 equal. So u1 equal to 0. Here u1 equal to what? We have to find out. The force is in this case. The force has to be given, right? So you have F2 is equal to what? The F2 will be given. Here F1 will be given like this. Okay. So how to solve those problems now? Okay. So we can solve any of these problems now. Even we can also solve this problem when you have. We don't know, but not only force, it may be that u1 is given and u2 are given, both are given, and then we have to find out that what will be the forces, f1 equal to what and f2 equal to what. This also we can find out. Yeah. It is possible also that any combination is possible. Possible that U1 is given and here the F1 is given, where U1 not necessarily equal to 0. U1 could be any value. Still we can find out what will be the value of U2 in this case. Yeah. So all combination possible. So very simple problem, but we can solve all kind of conditions. And how? So let's look at the simplest of the problem and like this one. Okay, the value here is k equal to 5 is given. Okay, let us say this is force, F equal to 3 Newton is given. Okay, this is a 5 Newton per meter. It is fixed like this one. Now we have to solve using the finite element analysis. And how to do it? Okay, first we will number the nodes. So node number 1, node number 2. Then, okay, this has only one element, so only one element, so element number 1. That's it. Now we have to put in Ku equal to F format, and we know that K equal to the big K is nothing but K minus K minus K, K, and then you have U1, U2, and then you have F1, F2. Okay, now what is the value of K here? 5. So the thing we have is 5, 1, minus 1, minus 1, 1. So I have taken 5 common because K is equal to 5. I've taken this common, multiplied by U1, U2, because this is the displacement vector. U1 is equal to 0 because this is fixed. So U1 equal to 0. U2, we don't know what the value is. This has to be found out, right? So we write U2 here because we don't know, is equal to. Now F1 and F2. F1 we know, we don't know. It's not given. It's not given, so we don't know. Whichever is not given, we don't know. Simple. You don't apply any Newton's law or anything. Okay. Which is not given to you is unknown. And this F1 is unknown. F2 is given. F2 is equal to, this is F2 means force which applied at node 2. And this is 3 Newton. So we write 3 Newton. And this is the equation. Yeah. So what happened? This problem is now in a matrix form. And this is what the finite element analysis is. Yeah. So we are writing for a problem which, to begin with, this is a discrete problem. This is not continuous problem. But still, even if you have a continuous problem, it is possible to have a matrix like this one, and what we will be doing in the whole class. Okay, the whole semester will be studying that only. Okay, now can we find out the solution now? Okay, now you have to solve, right? So you can see here, if you multiply this to this, what happens? 0 multiplies by this, and here also 0 multiplied by this. Simply what happens? There is no use of this. What we see, there is no use, because this anyway goes, makes it 0, this makes it 0. So this is no use, right? And finally what you end up with is minus U1 minus U2 multiplied by 5 equal to F1, where U2 is also unknown, F1 is also unknown. It will not help you anything. Yeah. So the first column, so simply we can say the first row and first column, yeah, in a way useless right now for the time being. Okay, so that's why we will not use it. What we will use, the remaining one. So what we did, the first one and this one, wherever you have 0 in displacement, that row and corresponding, if the row number 1, column number 1 will also go from this. And what you remains is just this. What? We will have 5, which is coming from here. And then you have 1. And then you have U2 is equal to 3. And this U2 equal to 3 over 5 equal to 0.6. You got the answer. U2 equal to 0.6. Okay. Now, once you have that, U2 equal to 0.6, now you can put the value here and you can get F1. Right. So now we write the whole equation 5, 1, minus 1, minus 1, 1. And then we have 0 and U2 equal to 0.6 that we calculated. F1, we find out F1 and 3 like this. Okay. Now, what do we get? F1, we can find out the F1 now, and that we can find out from the first one. Yeah, from the first row, and this becomes what? 5, 0, minus 0.6 equal to F1, or F1 equal to minus 3. Okay. Here, you have to be careful with the units, because matrix will not know what units you are using. So you have to put in the right units, compatible unit. Always use SI units to be, that will actually help you, So SI unit, you can convert everything into SI units and work. Automatically everything align, So F1 equal to minus 3. But since you have used a SI unit, so you can safely say Newton. So F1 equal to minus 3 Newton. And F1 equal to minus 3. Why? Because you have a reaction force. So the actual solution, if you have 3 Newton here, and if the 3 Newton here, and here if you have the 5 Newton per meter, right? And if it is a fixed here, so automatically the reaction force here will be opposite direction, which will be of 3 Newton, and hence you are getting it. Without applying any Newton's law, you are actually getting minus 3 Newton, right? Okay. So here, and what is displacement here? This will be U2. So U2 will be 0.6 meter. Yeah, because and positive, so it will be in positive x direction. Yeah. So this is how it works. Any questions so far?
No, sir.
Okay. We can now complicate things. Now we have only one node or only one element, not one node, but element. Now we can have 2, meaning that you may have a problem. Okay, no, before we go ahead, we can also now look at I will come back to that later, but let us say now you have a uniform bar of length L, area is A, right? And then this is, you can solve this also similar way. Let's say in our case it's like this. We are fixing number 2, node number 2. Yeah, node number 1 is given in force in this direction, where F is equal to, say, equal to 4 Newton. Okay. And then this is the length L, which is, and then is the area. Area, let's say 0.02 meter square. Okay. And L equal to 1 meter. Yeah. And E is given, let us say E is equal to, arbitrary, we are, since I'm doing, so write 5. Okay. 5 Newton per meter square, let us say. Yeah. Okay. So randomly I have chosen them. Now we have to solve this problem now. And what is this is a bar, uniform bar. You have to find out what is the displacement here, if you have this, like this one. Yeah. Now, as we go ahead, we will have a complicated equations coming into picture. We will solve the problem differently, because you have to also take care of if there is no uniformity in area, then what to do. Okay. Now this is one way here is to convert that into a spring, right? So that becomes a spring, and we have K here, and then you have force F equal to 4 Newton, and we have K equal to EA over L, where E is equal to 5. We will come back to this later. Actually, you can find out EA over L. We can let me maybe today only I will do this one. So it becomes 5. Then we have A is 0.02. So 0.02, right? Okay, and then over L. So E is 5, A 0.02 over L is equal to 1, and thus becomes 0.1, right? 0.1 Newton per meter. Yeah. So this is K equal to 0.1 Newton per meter. And then you solve it now, right? How will you solve? Okay, so now you have problem like this. We have K equal to 0.1 Newton per meter, F equal to 4 probably, 4 Newton, equal to 4 Newton, and we have to solve it. Now this is 1, this is 2. What we have is U1 equal to, we don't know, we have to find out. U2 equal to 0 because fixed. F1 is equal to 4 Newton, which is plus because in positive X direction. F2 we don't know, because either you know displacement or force. For node number 1, we don't know displacement, but we know force. In node number 2, we know displacement because this is a fixed, so U2 equal to 0, but force we don't know. That we have to find out. And you know that Ku equal to F. So K here is this K. Okay, so 0.1 multiplied by 1 minus 1 minus 1, 1 multiplied by U. U is U1, U2. So this U1, 0 is equal to F1 is 4 and F2 is F2. We don't know what the value is. Now, what we do now? We have 0 here, so this is useless, this line or this line, right? So this one, the second one, and this one, both. Yeah? So neither this will be used nor this will be used, yeah, because this will multiply by this and this to make it 0, right? So we will cancel this, yeah, and then we will cancel this. Okay, okay. Now what we get? 0.1 U1, 0.1 U1 equal to 4, and hence we get U1 equal to 4 over 0.1 equal to 40. Yeah, we get some numerical value, 40 meters. That's U1. Now, once you have U1, you can solve for F2, and F2 will be equal to, now go here, U1 multiplied by minus 1 multiplied by 0.1. So F2 equal to will be 0.1 minus 1, right, and multiplied by U1, which is 40, right, and that becomes minus 4 Newton. Yeah. So what do you get? The value displacement U1 you get equal to 40 meters, and F2 equal to minus 4 Newton, because you have positive direction, here it will be negative direction, and hence you get minus 4 Newton, and hence you solve it. Got it? Yeah. Any question, guys? Okay. Now regarding how you get K equal to EA over L. Yeah. So we get like this. So if there is a bar here, and then what is the strain? From here, a strain is equal to U over L, right? U is displacement. So if you have applied force here, let us say, and this is a U here, so a strain epsilon is equal to U over L is the strain, right? Now a stress, sigma equal to a stress. What is a stress? A stress equal to F over area, right? F over area, cross-sectional area is a stress. And then this is a linear material, Hooke's law, and what Hooke's law says? Hooke's law is equal to sigma over E strain. Yeah. Okay. And then that really means what? That tells us sigma is equal to F over A is equal to E times U over L. Right. Okay. And then means what? F over U is equal to EA over L. The force per unit displacement is equal to EA over L, and this force per unit displacement is nothing but is called K. So K equal to EA over L. Yes. So that means if you are given a bar, you can find out the equivalent stiffness, spring stiffness, and accordingly you can apply the boundary conditions as we work today. Same thing you can apply and you can do it. Okay. Now in the next class, we will talk about what is known as assembly of a stiffness matrix. And what is the meaning of that? Meaning is that you may have a spring, two springs or three springs together, right? And then what to do? Of course, this will be U1, this is U2, this is U3. And as far as again, we have to write in KU equal to F1. U is easy, you can write U1, U2, and U3. F is easy, you can write F1, so this is F1, F2, F3, so F1, F2, F3. But what about K? What is the corresponding K? That we have to find out. Yeah. So in the next class, we will do it. In that case, again, since U is 3 by 1, F is equal to 3 by 1, so K has to be 3 by 3. But how to find out that? What is the easiest way of doing it? Okay. From the first principle also, you can have the force induced at the force required at node I to induce a displacement at node J while keeping all degree of freedom fixed. From there also we can do it basically, yeah, but it is a lengthy process in that way. There is a even shortcut, fast shortcuts that we can do. Okay, that's what we will do in the next class. Okay, any question, guys? Next class,
No,
I believe
no.
on Monday, probably from 2 to 2:50. Yeah, most likely. Okay, guys. Okay. Thank you very much. Please,
Thank you, sir.
yeah, please read the book, solve the exercise problems, so now you will be able to solve a few. Yeah, so just look at that. Okay. Okay, guys.
Thank you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.